So if someone asked you why, when you let go of the slinky, does the bottom not fall, what do you say?
I'd say that there is, what you're doing, you're changing something at the top, and then there's a finite time for that information about the change to get to the bottom of the slinky. I mean, that happens even with a rigid bar, with a steel bar. It's just that the time is very, very short.
But a lot of people on the internet get uncomfortable with the term information. I mean, what are we saying by information in a physics sense?
It's a signal. So it's something, whenever you do something physically to affect a change, causality is, you do something and there's a cause and an effect. And between the two, information has to propagate, a signal has to propagate if they're not at the same location, physically at the same location. If you have extended systems, then to consider the motion of the centre of mass in an extended system, you only need to consider the external force that acts on the centre. Yeah, on the centre of mass, and that's gravity. And that starts acting, instantly that this is released. It's there to begin with, but it's suspended, it's held up. And then once you take away that suspension, that centre of mass has to start accelerating downwards instantly. So if you watch the movie, you see that the red dot indeed, it's a good test for the modelling, the red dot does start to accelerate.
And you didn't build that into the model, you basically allowed that to...
After the fact, I calculate, once you've got the model at each time step, I calculate where that centre of mass is, and it does indeed start to fall immediately. I think we were talking about this earlier, and you actually see the bottom of this thing start to rotate about now. So there's some kind of torsional mode, some twisting mode, signal that gets down to the bottom of the slinky first, rushes ahead, but it doesn't actually it doesn't release any tension clearly because the bottom just stays sitting there. It's only when all those other turns come down that that tension is relaxed.
Okay, so if you notice, the bottom of the slinky looks like it's just standing in midair until the top of it catches up with it. Okay, so the reason this happens because the only way that the bottom of the slinky can know when to start falling is when the tension in the line decreases, but the tension in the line can't decrease until the pressure wave catches up with it. And the pressure wave moves through the slinky at a finite speed. And so when you release the top, the pressure wave travels through, and as soon as the bottom feels that pressure wave, it can start falling. So I first saw a Slinky Drop movie from Veritasium, but they left out one critical point. They left out comparing where the center of mass of the Slinky is compared to when it drops overall. But you can also think of it that the center of gravity starts falling as soon as you release it. So you can't fool gravity. The center of gravity of the Slinky is actually falling at the same acceleration as if you dropped a ball at about the center of gravity height here. So it's easy to believe that the bottom of the Slinky can wait there almost weightless in midair as the top of the Slinky catches up. But what if we tied a weight to it, like a roll of duct tape or something? Would the roll of duct tape just stay there in midair while the top of the Slinky caught up with it? Let's check it out. Okay, now we're going to do a gigantic slinky off the top of my roof. And let's see how long the bottom of the slinky stays suspended in midair before the pressure wave of the top of the slinky reaches the bottom. So what's amazing about this is that the top of the slinky hits the ground before the bottom of the slinky, which was only a few feet off the ground.